Welcome to Differentials Applied Electronics. Right, here's our question. An electron whose mass is me moves at a speed of v. Its momentum is P equals mass times v, or mass times speed. The formula, find the formula for the approximate change in momentum, dp, resulting from a small increase in dv in speed. Okay, so we've got our original formula, P equals the mass times the speed. So we take the derivative of that, we get dp dv is equal to me. And if we want to know, put this equation in terms of a differential, we know that small changes in dv will create changes in dp. The change of momentum, and so our final formula is dp equals me times any dv. Just looking for the formula in this one. Right, next question. The induced voltage in an 8 Henry inductor varied according to V induced is equal to 3 times T squared minus T. About how much change in DI, change in current, occurred in the inductor current from time equals 2 seconds to time equals 2.01 seconds. So they're looking for the change in current in relation to time. So it's given us the formula V induced is equal to 3T squared minus T. If we remember back to our earlier lectures where we had the formula V induced is equal to, in terms of an inductor, V induced is equal to negative L, which is the Henrys, times di dt. So now we can just do algebra in this equation. We're just going to substitute the V induces or set the V induces equal to each other. And now we've got a di dt in the formula, and we can solve for di dt. And then we're going to move the dt over, and now we can solve for the change in I, where t is from 2 seconds to 2.01 seconds. Remember, our t is our starting time, so that's the 2 seconds. And our delta t, or dt, is equal to the difference of time. So we've got that time, the dt is equal to 0.01 seconds. Do all the math, and we find that we've got minus 12.4 milliamps. All right, the current in a circuit varied with time, t seconds, according to I equals t squared plus 3t. About what current change di occurred as t changed from 0.98 seconds to 1 second. Okay, so we're given I is equal to t squared plus 3t. Di dt, now we take the derivative of that, we get 2t plus 3. So now we just move the dt over. We've got di is equal to the quantity 2t plus 3 times dt. We put in our times. Our original time is 0.98, and our change of time, or our delta time, is 0.02. That gives us a change of I that is equal to 99.2 milliamps. All right, an increase in the apparent mass, Ma, of a moving particle occurs in accordance with Ma is equal to Mo divided by the quantity 1 minus V over C squared, and that all total quantity raised to the half power, where Mo is the mass of a particle at rest, V is its speed, and C is the speed of light in a vacuum. What approximate change dMA occurs in the apparent mass as a result of a small change dV in the speed of the particle? Express your answer as a formula. Okay, so this is kind of a big one to kind of unpack it. So we know that we want dMA versus dV. So the first thing I did is I take Ma is equal to the formula, and I raised the denominator up just to get everything on the same level. So when we raise it up, we've got to take the exponents, and we change the exponents to the negative power So the 1/2 power goes to the -1/2. That's that second bullet point there. Next, we kind of need to break up what's going on with the V. I'm trying to get V kind of by itself so I can see so I can then take the derivative of MA dV or dMA dV. And so we've got, the problem is we've got that V over C squared, so we're going to break that up and we're going to square both of those. So that gives us V squared times a 1 over C squared. So that kind of separates them out a little bit. It just makes it easier for me to do the derivative. And so now I can start doing the derivative. So this is going to be the product rule. So you can see we've got the MO multiplied by the exponent of the quantity. That gives us the -1/2 times the mass of the object or particle at rest. That's the MO. Times the original quantity raised to the power n minus 1. So we've got the -1/2 minus 1, which is 2 over 2, which gives us that quantity raised to the -3 over 2 power. And now the next part of the product rule is to do the derivative of the inside. And we can see that that's where we've got that the C 1 over C squared times 2. And then we've got the V becomes a V. So it gives us the 2 times 1 over C squared, and then we've got the V in there. Okay, now we can start trying to simplify that, and we can see that the -1/2 times a -2, that gives us a +1, so those can drop off, leaving us with the MO quantity, and then we're going to go to another page to finish this out. Okay, starting where we left off, we can take this MO here and multiply it over to the V. That gives us the second bullet point right there. Now, on the third bullet point, what we're doing is we're moving the first quantity that's raised to the -3 seconds power. We're going to move that back into the denominator. So C squared times that, and then we flip the polarity on the exponent. And that gives us our dMA dV formula, basically simplified formula. And now we're going to go ahead and take the dV out of the denominator and move that to the other side of the equation. So now we've got dMA in terms of small changes in dV. And this is the final equation that this question is looking for.